Hey everyone that's joining us now. Sorry we didn't get our streaming going, but you're here. Okay. All right.
I think we can get started because I think that the first talk is not important anyway. So.
Are you sure? It'll be yours. Okay, good. I think we can get started.
Can you hear me? Okay, great. So it's my great pleasure to be the chair, I guess, for this introductory or PQI 2020 Week 1 seminar series. We have very exciting list of speakers today. So our first speaker for the day, all three speakers, we have three speakers who are Dr. Jeremy Levy, Professor Jeremy Levy from University of Pittsburgh, Professor Amir Yacoby from Harvard University, and Professor Sara Majetich from Carnegie Mellon University. I guess I didn't introduce myself. I'm Gurudev Dutt, and I'm a professor in the physics department here at University of Pittsburgh. So our first speaker today is Professor Jeremy Levy. He needs almost no introduction to our audience, I think, because he is the director of the Pittsburgh Quantum Institute, and he received his bachelor's degree in physics from Harvard and a PhD degree in physics from University of California, Santa Barbara. And then his research interests center around oxide nanoelectronics, experimental and theoretical realizations for quantum computation, and a whole bunch of other things, including spintronics, quantum transport, nanoscale optics, and dynamical phenomena in oxide materials and films. He has won many awards. I guess he's a fellow of the American Physical Society, recipient of the Nano 50 Innovator Award, the NSF Career Award. He is National Security Science and Engineering Faculty Fellow, and he's also won several awards for teaching and research here at the University of Pittsburgh, which are the Chancellor's Awards. So with no further ado, it's I invite Dr. Levy to give his presentation, and I just wanted to mention the time restrictions. So each of you has 16 minutes. Professor Levy and Professor Majetich will have 16 minutes each, with 4 minutes for questions. Professor Yacoby, our invited speaker, will have 32 minutes with 8 minutes for questions. Okay, Professor Levy.
Thanks, Gurudev. You took, I think, half of my time, but that's okay.
Sorry.
No, that's all right.
No, I'm timing you from now. So.
Oh, well, okay. Yeah, no, I do want to thank the organizers, actually, the real organizers, Jenny, Barbara, who've helped to transform this event and try to do the most with, under the circumstances. So today I wanted to talk about some research that we've been very excited about, even like before, coronavirus. And actually, we're getting very close to a milestone, which I'll talk about in just a second. So the talk, I've not talked about this before, but it's really, I want to talk about the next dimension in a field that we've been trying to develop called correlated nanoelectronics. In case I run out of time, I do want to acknowledge all the people who've contributed to this work. I get all of my samples, essentially all of them, from Changbaum Ohm's group at the University of Wisconsin, and we've had really important theory collaborations, both at University of Pittsburgh and University of Strathclyde and Naval Research Laboratory. In my own group, been many people who have contributed to this area over the years. Today, I want to focus on thesis work of Dengyu Yang, who has been working on this area that I'll be talking about. So from the big picture is that we're working in an field that doesn't really exist at the moment, correlated nanoelectronics. It's a mashup of two well-established fields. So on one hand, you have semiconductor nanoelectronics, where you start with a 2D electron system and you gate it to create things like quantum dots, quantum point contacts, quantum wires, and so forth. They have interesting properties that come from the miniaturization and control over single electron spins and so forth. On the other hand, you have a whole class of materials, complex oxides, that exhibit a much wider variety of properties than semiconductors, like superconductivity, magnetism, ferroelectricity, and so forth. So what we're interested in doing is really combining these two very distinct fields. And we've begun our journey by doing this in two ways. It's sort of a perturbative intellectual perturbation, if you will. So one way of thinking about what we do is we take some chapter from quantum transport, some device architecture, and ask the question, what happens if you swap out the material? What if you put in a different kind of material? But you can also go in the opposite direction and say, well, we don't understand why this cube is floating. And so maybe we can take a device like something on the right-hand side and make it out of the material whose properties we don't understand and learn something new. So and we've also sort of begun to enter their non-perturbative regime as well. So the system that we're interested in is already, in some sense, a combination of these two paradigms. So this is a heterostructure made up of two insulating materials, lanthanum aluminate, strontium titanate, semiconductors. So what was discovered by Harold Huang in 2004 was that you could have a conductive interface, and the electrons are in the strontium titanate layer. There's a very sharp insulator to metal transition, but you also have all of the rich properties of strontium titanate that have been known for decades, like superconductivity, and the discovery of new ones like magnetism and strong tunable spin-orbit interactions. So the launch point for our research really began with the subsequent discovery by Jochen Manhart's group of a very sharp insulator to metal transition. So 3-unit cells of lanthanum aluminate does not produce a conductive interface, but 4 does. And so, and in fact, what they also found was that the 3-unit cell sample was metastable. So they could gate it from the back with 100 or minus 100 volts, and they could switch the interface between insulating and conductive phase. So I was fascinated by this, and we began to explore whether we could do this not from the back, applying voltage to the back, but from the top surface, where we could have higher resolution. So what we do to create nanostructures is first we have to bury electrodes into the interface to make electrical contact, and then we use a conductive AFM tip. And this tip is biased with respect to the interface, and we can sketch around. And what happens is that wherever the tip touches the surface, underneath the interface becomes locally conductive. And this is reversible in the sense that we can change the sign of the voltage and revert to an insulating phase. And we can use this to make a whole variety of different types of nanostructures with really high resolution. So the spatial resolution, ultimate resolution is about 2 nanometers. So with this, we've really sort of envisioned that we might be able to create a whole variety of devices, active devices, memory devices, quantum devices. You can see that this is a sketch, a vision from back in 2009. So we had never done low temperature measurements before, but we knew that this would be interesting. And so over the years, we began to explore more and more and develop capabilities, making transistors that work at room temperature, to making photodetectors, terahertz sources of emission, and then working with other materials like monolayer graphene, where we can define channels and make single electron transistors and so forth. And then start to look at some of the fundamental physics, like the mechanisms of superconductivity and how they're elicited in devices like single electron transistors and quantum channels and so forth. So, you know, as excited as we have been and busy creating nanostructures, they do have inherent limitations that are related to the technique for writing. So we use an atomic force microscope, and generally these are devices that can scan about 1/10 of a millimeter on a side. So there's also a practical spatial resolution, which is sort of given by the size of the wave function, which is low temperature is about 10 nanometers. The devices also decay. When we write them, they decay on the order of about 10 to the 3 seconds or so, maybe longer sometimes. And then we have a writing speed of about 1 micron per second. So we try not to go above that speed limit. So when you put that all together, you can get an estimate for the number of independent features that you can create. It's on the order of 10 to the 5 or so, which is great for one dimension, but not great if you want to make a big 2D system. So this has been a challenge and something we've been thinking about for a long time of how to get around these limitations. And so what we have developed over the last year and a half is a new approach to creating these nanostructures where we use an ultra low voltage scanning electron microscope. And so the idea is that there's no photoresist. So usually with E-beam lithography, you have a photoresist. There's no photoresist here. But we're going to use a low voltage, and that's important to prevent the damage to the samples. These are highly insulating samples, so you don't want to penetrate very deep into the material. So you want to use low voltages. So we believe that the spot size that is achievable is comparable to what can be done with an AFM. And also, we have a benefit that these devices are generally created in a reasonable vacuum, which also helps to preserve them. So my student Denia has been doing some tests on an existing system, for which we have maybe a few hours every couple of weeks. So she's been able to do some experiments to demonstrate that this actually works. So this is a trace of the conductance versus time as the electron beam traverses from one electrode to the other. You can see this sharp jump that happens. And this is all happening, much shorter time scale than what you can see here. But then we also checked by taking the sample out and putting it in an AFM that we could actually erase the structures, and they are reversible. So that suggests that the mechanism for writing is somewhat similar, messing with the adsorbed water on the surface. So she also did some resolution tests where you write two wires that have a gap in between them, and varying the gap a few times, we basically could determine that the spatial resolution was somewhere around 10 nanometers or so. So that's also an important test. It was also, we wanted to check that these devices that we were creating really had similar properties to what we could create using conductive AFM lithography. So we took one of these structures and cooled them down, and they do indeed show superconducting features that are very similar to the types of features that we would create using conductive AFM lithography. So finally, this is something that we're very excited about is we wanted to see if we could write through 2D layers. So we already know that we can create structures through monolayer graphene, and that's actually all we've shown so far for this case. But we're very heartened by the fact that we can create structures by writing. We have to increase the voltage and the dose a little bit to write through the graphene layers, but in fact, we can create conductive channels in the same way that has been done. And so we're very excited because we would like to work with HBN and so forth. So the outlook is that, based on the success, we've made a major investment. We have a Zeiss Gemini 450 instrument, which is arriving this Monday. We're really excited about this. We believe that we'll have like 10,000 times speed up with the respect to the conductive AFM lithography, with essentially no limit on creating devices. But we also believe that this is going to open up a new dimension in our research, being able to create 2D structures, as well as maybe even write through 2D layer stacks, like hexagonal boron nitride or bilayer graphene. So that's it for my talk. And any questions, I'll be happy to take them if there's any time left.
Yeah, actually, I think you have a little bit more time left in your talk itself. So, according to my timer.
I wanted to go shorter rather than faster, and I'm perfectly happy to yield my time.
But actually, Professor Majetich has a question. So I don't know if you want to say that.
Yeah. Hi, Jeremy. I was just
Hi.
wondering about what it took to write your, what layer were you writing, and what vacuum were you using for that?
So the vacuum was the standard vacuum in it was a Wraith E-line system, which actually also has a Gemini column, and that's why we were able to go to lower voltages. So the vacuum, I think like 10⁻⁶, something like that.
Okay, so reasonable vacuum, but what layer, like what was the voltage doing? What material, how general is this?
Well, I think you need to have something which is going to be conducive to switching its conductivity. So we were working with this LAO-STO system where we know that what the AFM does is it basically removes the OH minus hydroxyls from the surface. So we believe that that is happening probably in a comparable way that the electron beams has dissociating.
Right. So in terms of the physics of thinking about materials and what materials would work, you want something where the voltage that you can apply in the system that you've got with whatever vacuum, with say in the Wraith system, would let you change the density of states or change the chemistry of the thin layer.
Yeah, so what I would say is that I don't know how many systems can play this game, but what I would say is that this is a system now, it's a platform where we believe, we're optimistic that we'll be able to put a wide variety of 2D materials on top and gate them dynamically right below. So the idea is that if you can put your favorite 2D stack on top of the lanthanum illuminate, we'll be able to create nanoscale gates just underneath it. We'll be able to put, a volt over 10 nanometers, for example, really high electric fields. We may even be able to have, electrical contact and so forth. So I would say that if you can find another system where if let's say it works with an AFM, there's a good chance that it might work with an electron beam.
Well, I guess I've got obvious systems. I was thinking of the very thin cobalt iron boron layers that people have been using for voltage controlled magnetic anisotropy, where you actually are changing the oxidation state of the cobalt near the magnesium oxide interface in a tunnel junction. And it would be amazing if you could write that electronically. And
well, I'd be happy to try this out. I mean, it's easy to try it with an AFM. Like,
yes.
I would say the first dimension would be with AFM, and then if that works,
we do too. We do too. Right? Yeah. I'm just excited about it. Yeah.
Okay. So I guess we should conclude our discussion and thank our speaker. And I don't know if you can hear the claps with the mutes on most of the people, but so now we'll move on to our next speaker, Professor Amir Yacoby from Harvard University. So I'll just say a couple of words about this. So Professor Yacoby received his bachelor's in aeronautical engineering, master's degree in theoretical physics, and his PhD from the Weizmann Institute. He was then a professor at the Weizmann Institute. After a postdoc at Bell Labs, he became a professor at Weizmann Institute, and then has been a professor at Harvard from 2006. His current interests are in understanding the behavior of low-dimensional systems and their applications to quantum information technology. He has many varied interests: spin-based quantum computing, semiconducting quantum dots, color centers in diamond, topological quantum computing, and also interacting correlated electrons in graphene multilayers. So Professor Yacoby, and the topic of his talk is quantum sensing of quantum materials.
Thank you very much. Let's see. Yeah, I'm unmuted. So I'd like to start by thanking Jeremy and the other organizers for inviting me. It's a real pleasure, despite the fact that it's a format. I feel honored to be able to take part in this seminar series. And it gives me really the opportunity to tell you a little bit about some of the work that we've been doing over the past several years to explore new ways of looking at quantum matter. And I'd like to start by giving a little bit of motivation for why I believe it is still important to develop new measurement capabilities to explore quantum matter, despite the fact that we have quite an amazing toolbox already for exploring that. I'd like to give just a handful of examples of topics from the recent years to motivate a little bit what has been driving our effort. So for example, here I'm looking at ground state properties of various materials, and on the top right here we see a two-dimensional topological insulator. This is a material that has a gap in its bulk, but on its edge it has counterpropagating edge states, which means that there is no net charge current flowing along the edge, but each one of these edge channels is carrying an opposite spin species, which means that in equilibrium this system is carrying a steady state spin current. Unfortunately, currently we really don't have any measurement techniques that allows us to measure this steady state in equilibrium spin current that resides within such a topological insulator. So that would be an interesting motivation to try to develop something of this nature. Another example I'm showing here on the bottom left is a sheet of graphene subject to a strong magnetic field. And there, what we know is that this system behaves as an antiferromagnet. Despite the fact that there is a strong perpendicular magnetic field, the electrons would prefer arranging themselves in the plane. The spins are pointing in the plane. And unfortunately, if we wanted to know that a magnetic order of this nature exists in this material, we don't really have tools to do that. Neutron scattering, which is the standard technique to look at magnetism, will not be sensitive enough, because remember, the volume of the material here is 1 monolayer of graphene, and the magnetization density is perhaps 1 part in a million of what you'd find in a conventional magnet. So how would we know that this antiferromagnetic phase exists in the bulk? Now, going beyond the underlying ground state properties, we can talk about excitations. And here I'm giving 2 examples of interesting excitations that might exist in some recent topics. One is spin liquids. This is an insulating state, so any charge transport will not be suitable for us to explore. And its excitations correspond to spin-ons. These are spin excitations that behave as fermions. They carry an angular momentum, but no charge. And again, it would be very useful if there was a way for us to explore such spin excitations. On the bottom left, I'm showing here non-abelian, just a minute, 1 second. Non-abelian excitations. And here again, we lack tools to be able to identify and explore such non-abelian excitations. These would occur in materials such as topological superconductors. Now, if these excitations are long-lived, one can even ask questions about transport of such excitations. We can create chemical potential differences of such excitations and ask, well, what is the conductivity? On the upper right, I'm showing some recent theories showing that spin excitations in various magnetic insulators can behave as superfluids, which means that they can carry spin angular momentum over macroscopic distances with very little decay. And on the bottom left, we see some novel transport characteristics of spin, such as universal Peltier coefficients and Seebeck coefficients. And so again, how would we probe the chemical potential difference? How would we probe these spin currents in order to study these properties is largely an open question. So overall, we see that there's really a need to develop new experimental techniques, new measurement techniques. And in our group over the past several years, we've been focusing on a variety of topics and primarily developing new ways of looking at some of these materials. As Gurudev mentioned, we are interested in topological superconductors and developing new platforms for topological, for Majorana, for non-abelian excitations. I'll talk a little bit about transport of neutral excitations and their use to study quantum materials towards the end of this talk. We've developed a variety of novel scanning probe techniques like an electrometer, a very sensitive electrometer, And the focus of today's talk will be really some things that we've been doing using NV centers, a topic that Gurdev knows a lot about. I'd like to give just a few highlights from our research, not going into too much detail, but just giving you a flavor of some of the things that one could in principle explore. So as you'll see in just a minute, NV centers are a very good magnetic sensor. In fact, they can sense not only static magnetic field, but an entire spectrum of magnetic fields. And what I'd like to do today is to show how we can connect the measurement of magnetic fields in the time domain to various materials properties, such as magnetization that you might find, for example, in skyrmions, magnetic fields generated through electrical current flow, magnetic fields generated through spin excitations, the ones that I talked about previously, and also how to detect coherent magnetic excitations and to try to develop this into a novel scattering platform. So I'm going to be kind of very broad and just jump from one of these topics to the other without going into too much detail. And in the end, in the questions section, I'm happy to give some more details if there is interest. Just very briefly, NV centers are defects in diamond. You can see one here on the upper right. Their level spectrum is very simple. At some finite magnetic field, you can think of them as a two-level system whose energy separation depends on magnetic field. And one of the nice things about them is that the fluorescence of this system depends largely on which state it is in, whether it's in its ground state or one of its excited states. So this allows us to determine the spin state of this defect. And so you can think of this as a spin quantum bit that is fully controllable. We can prepare it in its ground state. We can control it on the Bloch sphere altogether to basically manipulate and use it as a very sensitive sensor of magnetic fields. Another advantage is that it is insensitive to temperature, so we can operate it in a wide variety of conditions that are suitable for the physics that we're interested in. And ultimately, the spatial resolution is really limited by the size of the defect, effectively, which is a few nanometers or a few angstroms actually, or by the distance of the defect to the object of interest, which is going to be in the range of, let's say, tens of nanometers. I already mentioned that we can use this defect to probe the entire spectrum of magnetic field, and this is done by cleverly controlling and pulsing microwave pulses onto this defect to prepare it and to manipulate it on the Bloch sphere in a way that makes it only sensitive to certain frequency sectors of the entire frequency band of magnetic field fluctuations that exist. For this talk, we're going to be using a scanning sensor. You can see it here in the middle. It's basically one that we make out of a monolithic piece of diamond. It is, we start out with a sheet of diamond about 30 microns thick, and then we thin it down and we fabricate these pillars out of this monolithic piece of diamond. And the end result is that we have one defect NV center sitting about 10 nanometers from the surface of the diamond. And this tip here serves both as an atomic force probe, so it allows us to know where we are from a topography point of view, but it also serves as a waveguide to extract the light that we need to collect in order to determine the spin state of our sensor. So I'd like to start to give the first example, and that is to see what is the relation between magnetic fields and magnetization. We're interested really in the magnetization. We're measuring magnetic field. The relation is not that trivial, it turns out. And I'm going to use the example of a skyrmion in order to demonstrate this. So here's the magnetization associated with the skyrmion. You can see two types of skyrmions here. One is a Bloch skyrmion, the other one is a nail skyrmion. And what characterizes skyrmion, and this is going to be important, is that the magnetization changes continuously from pointing, let's say, down at one place to pointing up at some further distance. And the key point is that it's changing continuously. It means that the angle between any neighboring spin is always very small. It turns out that you can prove that if that is the case, you can map out the pattern of magnetization, namely associate an angle on a Bloch sphere of each one of these spins, and you can map out this texture onto the sphere. And you see that this texture here specifically covers the sphere precisely once. And the reason is that, you know, the spin down here maps out to the South Pole, all the spin up here map out to the North Pole, and the spins in the middle, they will cover continuously the entire angular possibilities of the sphere. Because we demand that the spins change in angle continuously, this can be shown and proven rigorously that the coverage of this pattern must be an integer number. And that is what makes skyrmions topological. You can't have half a coverage. You can only have 0, which will be just a ferromagnetic state. You can have 1, you can have 2, but it can only be 1. And that's why these skyrmions are interesting, for example, from a storage standpoint. So here's some quick measurement of using fluorescence, so without any quantitative resolution, of how a material that should show skyrmionic structures looks like. At zero magnetic field, it shows domains here up on the left. And then at larger magnetic field, it will form into a skyrmion. And so we can map out now the magnetic field of this skyrmion to determine what the magnetization pattern is and map out this magnetization pattern onto a sphere to see whether it provides a unit coverage. And so what you can see here on the upper left is the stray field generated by this texture. On the right is a simulation based on the magnetization pattern that is shown on the bottom left that produces a magnetic field measurement that agrees extremely well with the measurement. And when we map out this texture onto the sphere, we indeed see that it covers the sphere precisely once. Now, the reason it's important to use the fact that this is a topological structure is that it turns out, and I'm not going to show this here, but it turns out that the problem of going from magnetic field to magnetization is not well posed. In fact, there are an infinite set of magnetization patterns that will correspond to precisely the same magnetic field measured. And hence, only those structures that provide the topological character are physical, and that allows us to select the right magnetization pattern here, showing basically a nail skyrmion as opposed to another candidate, which was the block one. So next, I'd like to talk about magnetic fields generated by currents flowing. And here you'll see that the relation between the current that we're interested in magnetic field is again slightly different. The physics problem that we're interested in is called hydrodynamics. We're interested to see what happens when a highly interacting electron system behaves as a viscous fluid. And this is a topic that started somewhere in the 80s in high mobility gallium arsenide and got revived when people started exploring graphene and realizing that this hydrodynamic behavior can actually survive all the way to room temperature. The premise for hydrodynamic physics is slightly different from what were customary in terms of electrical transport, here shown where momentum is continuously relaxed because electrons scatter off impurities, these star-shaped things, and only infrequently they scatter off one another. So momentum is not conserved in this problem, and this is what we know as Drude conductivity. That's what gives us the resistance. There is an opposite limit, of course, and that's the limit where electrons mostly scatter off each other, and they very rarely interact with impurities or phonons. Under these conditions, the center of mass conserves momentum and energy, and the system therefore enters a hydrodynamic regime. Hydrodynamics simply means that it has a conserved quantity, and that's total energy and momentum. And under these conditions, the system resembles what we know, the description from Navier-Stokes equations, etc., where in fluid dynamics or aerodynamics, where basically the interaction between molecules is dominant and boundaries affect the flow dramatically. So under these conditions, in the kind of pure hydrodynamic limit, if we had a channel and we'd ask, well, what is the velocity profile of electrons across this channel for a disordered or a regular kind of resistive type medium, we'd expect a uniform velocity profile shown in red. But for the hydrodynamic limit, we actually expect a universal profile known as Poiseuille flow, where the boundaries goes to 0 because of a viscosity that exist in the system, the friction between electrons lends itself to viscosity. And basically the velocity profile is shown here to be parabolic in shape. And so what we wanted to do is to use our quantum sensor, the NV center, to map out how the current is flowing in a 1 micron channel graphene and see whether this hydrodynamic pattern exists. So here you can see on the upper left in black lines is the shape of the graphene that we've studied, and the current is flowing from the wide channel all the way through the narrow segment down to the left. And what you can see in the box here is the relationship between the current and magnetic field. And this time there is a 1-to-1 correspondence between magnetic field and current. Here you can see a direct linear relationship between the components, but in momentum space, namely, if we map out all magnetic field across a plane, Fourier transform it, that would correspond to the Fourier components of the current flowing in the channel. And you see that Bx corresponds to Jy and By corresponds to Jx. And this can be seen very nicely in the two upper plots, where on the upper left, we're plotting Bx, and you see that that is due to only when there is a Y current. And here on the right, we have By, and you see that that shows up only when we have an X current. And in the bottom, you can see a full quiver plot showing the direction of current and its intensity, and you can already see that the current is fading away at the boundaries. In fact, if we use our probe to take a high spatial resolution with 30 nanometer spatial resolution of the current profile, you can see in the red dots here that indeed the current profile is very highly non-uniform and resembles pretty much this Poiseuille flow. In comparison, if we look at a disordered graphene sample shown in yellow or a palladium wire, both which are normal Drude type resistors, we see a very flat type resistance profile. So this is very nice. This is all done at room temperature, showing that indeed we can use our quantum sensor to get direct insight to how current is flowing in these channels and get some direct indication to the importance of electron-electron interaction in this dynamic property.
The question.
Yeah.
So can you see other manifestations of the hydrodynamic flow, like turbulence are there other types of structures like vortices and other things that you might see in the future?
Yes, there have been quite a few predictions, quantitative predictions of how to, in order to be able to see these kind of vertex and whirlpools that you would expect. So these should be present. And these are experiments that are being designed. We may want to cool this down a little bit because hydrodynamics here requires us to work in a very narrow channel. But if you cool down, you can extend the width and give the flow a little bit more room to develop these interesting flow patterns, but absolutely.
Thanks.
So in the introduction, I talked a little bit about magnetic excitation. So I'd like to spend a little bit of time to show how we can measure such magnetic excitation and also to motivate some of the interest in this phenomena. So what we're really interested is in looking at a magnetic insulator. I mentioned already that in such magnetic insulator, you can have superfluid spin transport in this system. And so the question is, what would be its signatures and how could we possibly monitor that by measuring magnetic fields? I want to first point out that the idea of spin excitations behaving as a superfluid is a very old idea. This is actually a seminal paper by Bert Halperin and Pierre Hohenberg from 51 years ago, where in their abstract they write a hydrodynamic theory of spin waves is developed for certain magnetic systems in analogy with the derivation of two-fluid hydrodynamics for liquid helium. So this is kind of a very concrete theoretical model that is applicable actually to a large variety of existing magnetic systems that shows that these systems should behave very, very much like superfluid helium. So what are these spin excitations? So we of course know that if we have a magnetic insulator and let's say the spins are interacting through exchange, the spin waves are basically the spins pushing on one another, and they're basically moving like a field of straws, and as the wind is pushing on them, you can see how these straws are bending. One interesting thing about these systems is that if there is an anisotropy in the system, and the anisotropy could either be intrinsic, structural, or it could be external using an external magnetic field, they develop a gap in their excitation spectrum. So here I show the excitation spectrum, energy versus momentum of these spin waves. And there is a gap here, and the gap is given by what's known as the Kittel law, which basically tells you that below this energy scale, you cannot have any spin excitations in the system. And this will be extremely important because remember, if you have a Bose system and the Bose system condenses, what happens is that there will be a macroscopic occupation of the lowest energy possible state in the system, but not beyond. So we know how to measure precisely where this gap is, and we're going to also measure where we're going to measure the chemical potential of these spin excitations, and we're going to see whether we can see signatures of this condensation. So just several general properties of a superfluid is precisely that if we were able to measure the chemical potential of these excitations, then as a function of density, we would see an increase and then a saturation at the bottom of the band, because at that point, macroscopic occupation of this lowest level will start occurring. So using the NV centers, it turns out that we can measure directly the chemical potential of spin excitations. Basically, what these spin excitations are doing, they're creating fluctuating magnetic fields. And if we measure the correct portion of the spectrum of spin fluctuations or magnetic field fluctuations in the system, we can easily extract with no unknowns. These are both measurements that we can do, the rates of decay of the NV center under two different conditions. Omega ESR is the level spacing of the NV center, and we can extract directly what the chemical potential would be. And here you can see a plot of this chemical potential. That's the vertical axis measured in frequency versus a magnetic field, and the number of magnons, the number of spin excitations that are being pumped. And what you can see is that as you're pumping more and more excitations, the chemical potential rises from 0, but then always saturates precisely at the bottom of the band, shown here by the black line. This is the Kittel law that I showed before, and you cannot have this chemical potential rise above it. And that's a very nice indication, at least consistent with the idea that the system is macroscopically occupying this ground state in the system. All right, the last topic that I'd like to talk about is using the ability to measure these spin excitations, this time coherent spin excitations, as really a new platform for probing materials. So what are some of the scattering techniques that we are familiar with for exploring materials? We know of X-ray scattering, neutron scattering, just optical scattering. The idea in all these techniques is that we have a source. This source produces coherent waves of particles or waves, both the same thing, with a given energy and momentum. These coherent waves or particles impinge on a material, a target of interest, and then they diffract. And the nice thing about scattering theory is that we don't need to measure the interaction region itself. What we measure is far away. We measure in the far field the intensity of the scattered waves. Ideally, if we can measure both intensity and phase, amplitude and phase, then we can use that to reconstruct some property of the material. Neutron scattering will reconstruct the magnetization textures in the system. X-ray will reconstruct structure, etc. So what we'd like to do is we'd like to see if we can reproduce the same ideas only with coherent spin wave excitations. So the vision is to consider this gray slab here. This is a magnetic insulator. We use YIG, yttrium iron garnet, 100 nanometer thick. And it has been shown, and you'll see in just a minute, that this material can support very highly coherent spin wave excitation that are very long-lived. They can propagate for millimeters without decay, and they have a very well-known dispersion. And so we're going to excite them using some microwave antenna shown here in the yellow on the material. These waves are going to propagate. they're going to be impinging on a target material. This target material could be layered materials, could be any material that we choose to put on this material. They will be diffracted, and we're going to use the NV center in the far field to measure the diffracted waves. You'll see that we can measure both amplitude and phase of the scattered wave. And then we'll use some theoretical analysis to try to reconstruct some properties of these materials. So what we really need to make this work are four basically ingredients. We want to be able to demonstrate that we can launch coherent waves. This in fact has been demonstrated in years by many different techniques, but we'll show it here as well. We'd like to be able to detect these waves. This again has been done with various techniques like brilliant light scattering. Will show that NV centers are a very useful technique for detecting both amplitude and phase with high spatial resolution, allowing us in principle to go down to very short wavelength magnons. We'd like to see that there's an appreciable interaction between the waves and our target. And then we'd like to be able to reconstruct from the scattered wave what our source material is. And you'll see that that's, at this point, is still the most sketchy part in the entire process. So here's an image, and I'll explain how we obtain this image in just a second, of the propagation region. I call this the vacuum region. So spin waves do not propagate in real vacuum, unlike neutrons or X-rays. They need the medium. So here they're propagating in this YIG. YIG is kind of a very well-known material, but we can image the propagating waves. These are not scattering waves, and this is a movie of propagating waves of magnons. They have in this particular movie a wavelength of about 4 microns. We can tune it down all the way down to a few hundred nanometers at the moment, but we're working on tuning it down even further. And the idea is that if one positions our NV center at any point in this vacuum region, it sees a magnetic field due to these magnons that are shown down here. There is some intensity, and it's oscillating in time at a frequency omega. And it has a local spatial dependent phase that's given by the wave vector. And the frequency here, omega, is simply set by the frequency of our drive. So in order to drive magnons of a particular frequency, we will send an oscillating current through our antenna here on the YIG that will generate an AC magnetic field at this frequency. This will launch the magnons. And you see that the phase depends on position. Now, those of you who remember how the two-level system behaves under a time-varying drive, you remember that the axis of rotation of the two-level system depends on this phase. So whether it rotates around the x-axis or the y-axis will depend on position. Now, if we only measure the fluorescence, so the projection on the z-axis of this spin, that's not going to be enough. So in order to determine the axis, what we do is we send another microwave signal that this time only affects our NV. So it's a uniform field in space. It does not generate any magnons, but it drives the NV as a reference. And so you can imagine now in the rotating frame that we have two drives, one that is fixed, the other one is position dependent, and its phase is changing. And what you're seeing here is the constructive and destructive interference of these two things. And whenever there is a destructive interference, that's these bright spots. That's precisely tells us when the phase here is a -1 compared as a pi. So we can read off, in fact, just by doing this, we can read off precisely what the wavelength of magnons are at any given frequency and map out the dispersion, for example, at these. Next, we can do a measurement of what happens in the far field. So this is what I call only an amplitude measurement. So the white circle is our target. Specifically, our target here is permalloy. So it's a different type of magnet. And the magnons are scattering off of this. And you see that the intensity of magnons is varying in space in an interesting pattern here. And we can turn on the reference phase to also extract the phase of these magnons. And so in practice, what we're doing now is we're looking only at the far field out of these two measurements, the amplitude and phase, and we'd like to reconstruct the source. And I'm not going to go into detail. I just like to show that this is actually a very hard process. In fact, obviously, if there was no noise and we knew precisely the properties of these magnons and their dispersion in the material, we could inverse, basically just knowing the amplitude and phase of the scattered waves, we can reconstruct uniquely the source. Unfortunately, there is noise and there's always deconvolution, and this process is not very easy. So what we're showing here is basically assuming some target. We calculate what the scattered wave patterns and amplitudes should be, and we're minimizing some source function to find a best solution. And what you can see here is a dipole source. And if there's time in the question, I can explain why a dipole is the correct way to think about this source. It produces more or less a similar scattering pattern, but the amplitude is a little bit off. Here we add the next moment, which is a quadrupole for our source. And you can see that we're reproducing a little bit better the amplitude as well as some of the details in the phase maps. So this is going to be a work in process. It's going to take us time to figure out how to properly reconstruct the precise material. But even here, you can already see that to some extent, there is more information in the measurement than there is in the theory. So it means that our theory is still lacking, and we would need some more work to figure out what is it that we're missing in our ability to describe this source. So with this, I'd like to just summarize and highlight the contribution of many of the students, postdocs that have contributed to the various projects over the years. They're shown here. I'd like to also highlight very fruitful collaboration with several groups across the world. Thank you for your attention.
Okay, thanks for it. So I can open this up for questions. I think I saw a couple of questions in the chat from Dr. Majetich. So.
Okay, you had a point with the dot underneath your tip. What is the dot made of?
So our target is permalloy. So it's
permalloy. Okay, but then what does the fringe field of the permalloy do to the local excitation around the yig below? That's going to be huge.
Right. So you can see already. So you can see I've not talked about this, but you can see in both the amplitude and phase map that there is some magnetic field that we will pick up in the near field. And so yes, indeed. Okay, indeed, the spectrum of excitations of magnons in this region will change because of the presence of the yig. But that's actually part of what we're interested in extracting. Now remember, the DC behavior of this system is not what's being probed. We're basically applying a time-varying magnetic field on the yig, and we're seeing how that yig at this frequency and wavelength is responding to that excitation, and it's basically generating another source of magnetic excitations in the yig that then are interfering with our incoming waves. And that's
okay, how do you do the control experiments? I'm just not understanding completely what you're doing.
There is no control experiment, right? Basically, it's you know, think of optical diffraction, right? You have you're sending a beam, you're shining a laser beam. It has a wavelength and it has a frequency. Okay. And you're looking at the diffracted signal far away, and you have a theory that tells you what the structure factor is, basically how these waves interact with your matter. Okay. So I can explain a little bit more what goes into our theory that describes the interaction between these spin waves and our target, this case, the yig. But basically what happens is that this interaction leads to secondary waves that are generated, and these secondary waves interfere with the incoming waves to give us these patterns. And so by measuring these patterns and knowing what the interaction, so to understand the interaction, just suppose I had just one magnetic moment sitting on the surface of yig. Okay. And you can ask, well, how would this magnetic moment respond to the spin waves? And we can write just Maxwell's equations, and it will tell us precisely how this magnetic moment interacts with this. It tells us about the magnetic susceptibility of this target. And that susceptibility is responsible for generating these scattered waves that we measure.
Okay, so the spin waves are exciting the permalloy, and then the permalloy is exciting your NV center.
Is exciting the YIG again. We're measuring the total response of the YIG downstream, and we're measuring that with the NV center, yes.
Okay, thank you.
So I thought you did show a control where you scanned over the region before the permalloy, right? That is the actual wave that's propagating into the permalloy.
Correct, yes. So in this region, indeed, and it's interesting, you can ask, well, why can't we see backscattered
I was
waves?
going to ask that. Okay, yeah.
Right, but so this is an interesting property of YIG and the spectrum of spin excitations in it. But yes, you're right. This is a region in which we have no scattering taking place, and we can see just nice straight wave fronts propagating at a well-defined wavelength and frequency. The reason there are no backscattered wave is because these are what's called surface magnetic excitations. They're Damon-Eschbach modes. And because this medium breaks time reversal symmetry, the forward propagating waves live on the top surface. The backward propagating waves live on the bottom surface, and we're very weakly sensitive to them. They're much further away.
I see. I had a question about your chemical potential experiment. Do you think it's possible that magnon scattering, for example, and so on, would that, could you tune it, similar to BCS, BEC type experiments? Do you think you'll see any signatures like that with these experiments?
Yes, I believe so. So we haven't done this experiment, but there have been experiments done using Wilwen light scattering where you do what's called parametric excitation. So you're using light, which has very little momentum, but at an energy that's twice the minimum energy to excite an excitation. And so simultaneously, each photon gets generated into two magnons that has plus and minus wave vectors. And what they were able to show is that indeed you have macroscopic accumulation of magnons at these band minima. And they were also even claiming to say that they could see a spontaneous phase emerge. So, macroscopic occupation is not enough. If you want to really argue superfluidity, you want to show that there's an order parameter, there's an amplitude, well-defined phase. They were claiming that there's a phase.
Do you expect something like that? Is there like a conservation of magnon number or something that helps you to?
No, unfortunately, there is no. So there are a bunch of non-conservations. So one, spin is not conserved. So unlike superfluid helium, where mass is conserved, helium atoms are not going to go anywhere. Spin can be lost through, for example, an orbit interaction to the lattice. So first of all, it's not conserved. But indeed, it is conserved to a very large degree. Second, you can have magnon-magnon scattering. And in fact, I didn't mention hydrodynamics of electrons. In fact, magnon-magnon scattering is very, very strong and rapid. And you can have two magnon in, two magnon out. You can have two magnon in, one magnon out. So there are a bunch of processes that are allowed for magnon scattering. And in fact, there are interesting predictions about magnon hydrodynamics. So hydrodynamics is not something that's limited to molecules or electrons, any particles. In fact, there's a lot of discussion in the literature about hydrodynamics of phonons as well. So that would be interesting to explore.
I have a question.
Yeah, please.
So again, getting back to this hydrodynamic regime, looking forward to seeing that paper. It hasn't come out yet, right?
It's, I think, in press, something like that. It's on the archive, though. Yeah.
Oh, okay. Yeah. So I was wondering if you're what you think the prospects of seeing these Diakonov Schur, microwave oscillations. It would, I guess you have to change the geometry a little bit, put a little side cavity or something. Is that something that, it also seems like it might be conducive to, NV detection, if you can heterodyne.
Yeah, I agree. I think it falls in kind of the right frequency range for trying to see some of these things. With NVs, there's always the complication that if you want to tune frequency, you need to tune magnetic field. Now, under most conditions, the magnetic field that we're dealing with here, I think that will not influence the physics that you were mentioning, but there is this complication that one needs to remember.
Right.
But yeah, I think this would be a very exciting thing to explore.
Can I ask one more follow-up, which is if you talked at the beginning about topological effects, and so since this is a two-dimensional in the last experiments, is there any predictions of topological magnons or in different materials that you might be able to study with the NV centers?
So the fermions themselves are topological, but they're the ground state, they're not the excitation. It turns out that they have very interesting excitation spectrum. People have predicted what would be kind of the magnon spectrum. How would these textures fluctuate when excited? So this would be one interesting thing to explore. There is even a magnon Hall effect. Basically, if you have an electric field across your sample and you have a flow of magnons, you will see a chemical potential imbalance in the number of magnons on the two sides. So there are a variety in materials that have spin-orbit interaction, for example. There are a variety of interesting physics that I think can be explored. We're kind of trying to get the low-hanging fruit first, but yes, a lot of really interesting stuff to think about.
Okay. All right, I want to thank our speaker again for a very exciting talk. And I think we'll move on to our last talk of this session, which is by Professor Sara Majetich from Carnegie Mellon University. And she has been working in, she is a professor at Carnegie Mellon. She was she earned her bachelor's degree from Princeton, her master's from Columbia, and her PhD from the University of Georgia. She's also the recipient of many distinguished awards, such as she's a fellow of the American Physical Society and the Electrical Institute for Electrical and Electronic Engineers. She won the Eminent Scientist of the Year Award and National Young Investigator Award. And she is also a IEEE Magnetic Society distinguished lecturer, and she has won various awards at Carnegie Mellon for teaching and advising as well. Her research focuses on fundamentals of magnetic nanoparticles that have very uniform size for applications in information storage, processing, and biomedicine. And she studied these using many different techniques. And she's going to talk today about magnetic tunnel junctions for classical and quantum computing.
Thank you, Gurdeep. Again, this is a talk that's more on the applied physics side. That's where our expertise is. Thank you for bearing with us and staying for the end of this session. What I want to explain is a little bit about what our capabilities are, what we've seen in classical magnetic tunnel junctions, and how that could be related to other types of tunnel junctions for quantum computing. So again, these are my students that I've been working with. And let's go back. Oops. Okay. So the real interest that we have is thinking about neuromorphic computing. So whether that is quantum computing, whether that is classically inspired neuromorphic computing, what we are looking at is the example of the IBM True North, where they model using magnetic tunnel junctions, 1 million neurons to be the synapses But one of the issues is that it still uses a huge amount of power compared to the brain. And I'm sure I don't need to explain to quantum computing people the advantages of going to more energy efficient methods. But we are not restricting ourselves to solely pure quantum computing bits. There's a lot of computation or competition from memristors, which have electrical resistance with complex oxides used for the synapses, and there's lots of crossbar technology, and people are using this. But one of the issues that is opening up the possibilities for quantum computing is what we call the internet connect problem, that if you have to wire up every little device with crossbars, you can individually address lots of different tunnel junctions, but the I²R power losses just in getting to address a particular device are getting bigger and bigger. And this is leading to a big problem with just the energy use in any kind of information storage. And so that opens up possibilities for more complex approaches or more novel approaches, including what we are looking at, which is reservoir computing, where you have one input and one output and a very nonlinear medium in between. That medium could be quantum, that medium could be classical, but this is a simulation that was done, whoops, sorry, based on magnetic tunnel junctions. And it was based on having a magnetic pattern, which is shown on the top. Sorry, I'm just not getting through. Oops. Okay, on the top, which is shown between the input yellow dot and the output yellow dot of magnetic domains, either magnetized up or down. And this is a kind of a random pattern, but completely classical, of a magnetic thin film. And because of magnetoresistance being different by a large order of magnitude, depending on whether spins are parallel or perpendicular, you have different magnitudes of current pathways, which are shown in the bottom slide, showing that the pattern is very nonlinear between the input and output. In this case, it's looking at a sample that has skyrmions, but it would not have to be a skyrmion as long as it is some sort of, sorry, very nonlinear behavior between input and output. And so this is completely classical, but it would map onto something that was quantum in terms of input to output being very nonlinear. So what our strengths are is that we do a lot of nanofab. And so one of the things that we've done is to make lots of pattern nanoparticles. And we've done this on Hall crosses, and we use conductive AFM, which Jeremy Levy mentioned earlier in the session. But in this case, we use it to look at the magnetoresistance locally as we look at particular tunnel junctions. And so we can get current maps going through individual tunnel junctions that are different sizes. So the smallest is on the top here, smallest is on the bottom here. But what we're able to see is we can tell whether they're, for a particular size, whether they're in the parallel state or the anti-parallel state, in which case we've got two different amounts of currents that are getting through. And that is true for all of the different sizes. And we can measure down to 20 nanometer devices here. We can actually get down to about 10 nanometer devices. And one of the things that was mentioned earlier was using current to switch, using spin orbit torque, using quantum mechanics. We have been able to demonstrate the smallest spin orbit torque switching or spin Hall effect switching of a nanopillar, which was 20 nanometers. Oops. And now what we're wanting to do with that to move forward is to use these Hall crosses and our capabilities with conductive AFM to identify and to switch and to tell we've switched with individual devices to, oops, okay, to then look at what we can do with that in terms of the physics. And one of the things that we're very interested in right now is using this for stochastic computing. So again, this is very classical, but would extend to quantum. But the theory here is that we look at coupled magnetic tunnel junctions, shown here, with some feedback circuits. And there's lots of theory about what would happen as these are coupled together so that these could act as stochastic logic gates. So in terms of probabilistic logic gates, the advantage is that it would be lower power than deterministic logic gates. In terms of other advantages, it would be completely reversible, and that's of great interest for decryption. So people like DARPA are very interested in this. And, oops, sorry, I'm just not doing this very well. Okay, so we are actually making these devices, making hardware devices. In the center of each of these little flower-shaped structures is a magnetic tunnel junction. We make little chip carriers. We actually hook these up and look at the logic gate behavior. And let's see. Okay, so we can tune these in looking at the high resistance anti-parallel state, the low resistance parallel state as a function of the bias voltage, looking as a function of time. We can look at this directly. These are in the microsecond time scale, but now our current time scale is down to a few hundred nanoseconds. And we can do this. And one of the things that we're interested in doing that I think is relevant to people interested in quantum computing is this idea of reservoir computing, which does not require anything quantum. It just requires a series of inputs connected to a reservoir that is strongly interconnected, very nonlinear, but then connected to an output. So for the people who are familiar with large data sets and machine learning, all of these, all the mathematics for these techniques have been worked out. But what is different here is that we could make the hardware for the reservoir computing based on interacting magnetic dots or other related structures that have magnetoresistive or electronic properties that change with time and are also coupled together with one another. So that's something that we're working on right now. We just got a new NSF grant for. And one of the things that we're looking at is demonstrating an invertible logic gate, again, based not on the deterministic kind of logic gate, but on the time average probability. And that's where we look at our particular magnetic tunnel junctions and what is, again, there's a lot of information here. Don't want to go through the details, but basically we can tune with the voltage what is the average lifetime in one state parallel versus the other state anti-parallel, and we can tune that one way or another with the voltage, and therefore we can do analog multiplication, we can do all kinds of processes faster based on looking at the curve of what is the time average of magnetization versus bias voltage. And we've built some circuits, but I just wanted to finish with something that's a little bit more of the quantum mechanical direction that could be followed with these tunnel junctions. And that is based on work not done by us, but by Mike Schneider at NIST, looking at quantum magnetic Josephson junctions, where they have Josephson junctions and they have deposited a small amount of magnetic ions inside, and then they anneal that to grow into little clusters, and they're able to tune the switching field for the Josephson junction. One of the things that is really interesting to us is that they're able to get, we're able to see on hundreds of nanoseconds. They are, at least in simulations, able to get down to a few picoseconds. That's not been measured yet. There are lots of questions about what is actually going on. These are their cartoons from their Science Advances paper. I think it's a little bit more complicated than that, but I think that there are a lot of possibilities for coupling these magnetic tunnel junction devices, whether they're Josephson junction magnet devices, whether there are very small, more classical devices with quantum mechanical tunneling in between them. But I think that there's a lot that could be done that is of interest to this community. So anyway, I'll just stop there.
Okay, so I open up for any questions first from audience. Anyone has questions? So were these all room temperature experiments that you were showing us? Or do you have
Other
to cool
than
them?
the Josephson junction ones, they're all room temperature. Yeah.
See, and these materials, you make them out of depositing on silicon, or I missed
they're
that.
very, very standard cobalt iron boron, MgO, cobalt iron boron. These are the same materials that are used for or being explored for MRAM, but we are looking at a different regime where, again, so these are very manufacturable devices. They work at room temperature, but we are looking at a different regime, looking at more probabilistic effects with the idea of moving towards what kind of probabilistic effects basically building the capability to detect at lower temperature and with quantum materials.
I guess I missed the whole reservoir computing angle exactly. So is it that, is reservoir computing?
Yeah, so with the reservoir computing, and again, this is a CS thing. This is not a physics thing. Yeah. But with the reservoir computing thing, the machine learning people, they would say, like, we don't care what goes on in between. We have some inputs. We want to see how those inputs correlate with outputs. Like for physicists, you would say, like, oh, it's kind of like linear algebra. Right, you just want to see, like, what are the correlations? You don't care why they are in the beginning, but of course, if you're wanting to build on that to go further than just solving a problem, you're going to want to change the weights of what is in the reservoir, and that's where the ability to tune the weight for a particular state with the voltage
dynamically
is important. Yeah. Or it could also be tuned just based on magnetostatic interactions or from Josephson junction tunneling. I mean, there's lots of ways that you could engineer interactions within the reservoir. And I think this is a real possibility for our community in looking for something that could connect real quantum computing, the CS people that we know who have all kinds of theories, and actual physics devices that we could design and measure and test and optimize. So I think that's this reservoir computing idea is something that right now is just all software. But in terms of building the hardware that is based on a more quantum devices, I think that's a real opportunity for our community.
I have a question also about this reservoir computing idea is very interesting. I was wondering how the connectivity scales. Like if you think of it as a matrix, is it a sparse matrix?
Yeah, well,
yeah.
Right now, like in CS, like it doesn't matter. You can be like 600 devices all connected to each other. Physically, that's not going to happen. But that's where the nonlinearity is really important. And right now we're pretty good at making 2D arrays of devices. Some people are better at making 3D. We could think 3D, but I think in building and designing and testing 2D connectivity, for example, you don't get Arrhenius law behavior if you've got magnetostatic interactions. You're going to get other kinds of statistics, and quantifying them and figuring out how to design the connectivity. We're actually making little arrays of devices where we make lines of devices, 3D dots, a range of this, and just looking at the statistics just to see how what is needed to couple and how do you perturb. And with the whole idea of reservoir computing, what you want is a system that is as nonlinear as possible. And so it doesn't mean you want an ordered array, but you want to understand how to treat those statistics. So that's what we're looking at right now.
Okay. Are there any other questions? I don't see anything in the chat. So if not, then I guess I'd like to thank all our speakers for today for a very inspiring and interesting session. And I just wanted to ask Kay and Jenny, I wanted to thank them for organizing this, and of course, Professor Levy for putting this back together along with everyone at PQI. Is there any announcements that either of you had for our next week, or anything that we want to say anything here? Or
well, this is our weekly thing, so yeah, tune in next week.
Tune in next week. Yes, exactly.
But yeah, thanks Amir.
Thank you.
Thanks Sara for leading off of this, and yeah, looking forward to seeing all of you next week.
Thanks, Gurdev.
Bye.
Yeah, thanks Gurdev for
it's nice to be connected even in this remote way, at least. Yeah.